With a great pleasure, I introduce our next speaker, Professor Vera Serganova from University of California, who will tell us about odd nilpotent adjoint orbits for Lie superalgebras.
Hello, can you hear me?
Yes, we hear you.
Okay, so thank you for inviting me. I will try now to share the screen. Oh, sorry.
Okay.
Can you see the screen?
Yes, we see your presentation.
Is it good enough, big enough?
I think it's big enough.
Yeah, I can. Yeah, I'm not at home, so I'm a little bit not an unusual environment for me. So thank you very much for inviting me, and I'm actually admire how you organize this conference despite all the war, and I support you very much. And today I'm going to talk about my joint work with Ina and Weisenblatt, and it is about superalgebras. And what we are doing, we're studying odd nilpotent orbits in superalgebras. And let me start with my presentation about them. So what is the problem we are going to discuss? So we assume we work over C, or actually algebraic closed field of characteristic 0, doesn't matter much. And we consider finite dimensional superalgebras with one additional condition that it is quasi-reductive. So that means that if my superalgebra has even an odd part, then the evenly algebra must be just reductively algebra. And the odd part is semi-simple as a G0 module. So it is convenient to consider the algebraic group G0, usual algebraic group, such that its Lie algebra is the even part of a superalgebra we are talking about. And we would like to study the orbits of this algebraic group in G1. So what I'm going to talk today, we have a lot of classification results, but I would like to talk today about some analogs of two things. In the classical situation, if we study joint representation of reductive Lie algebra, there are two important things. We have Jordan decomposition, and we have Jacobson-Morozov theorem. And somehow, in some way, similar things or some analogs of this exist for Lie superalgebras. And actually, I would like to see so we all know that nilpotent cone in the reductive Lie algebra is a very important object for representation theory in many ways. So I would like to show in my talk how the geometry of G0 orbits in G1, how it plays a role in representation theory. So we consider, actually, it is convenient to talk on the language of algebraic supergroups, but essentially what we are doing, we fix this G0, which is an algebraic group, associated with Lie algebra G0, and we consider representations of G, finite dimensional, say, representations, such they're integrable over G0, so they really are rational representations of the even part of G0 of this algebraic group. So this category is a tensor category, and what is important, what is also Frobenius, and it's quite non-semi-simple in general, and it is interesting to consider finite dimensional category of finite dimensional representations, and it reminds very much the category of representations of finite groups of the field of positive characteristic. So what we are doing next, we consider any odd element here. And it generates an abelian superalgebra. So usually it is one-dimensional superalgebra. So I take X and I take S commutator with itself. And by Jacobi identity, X is 0. And now we consider the minimal algebraic supergroup G of X inside G, whose Lie superalgebra contains this element. So by the same argument, it's clear that this supergroup, since it's algebraic, its even part can have a dimension bigger than 1, but its odd dimension is always 1. So the idea is to understand information about G module M using the restriction of these modules to these subgroups G of X. So let me discuss a little bit examples of quasi-reductive supergroups. So the simplest example we can think about, if we start with a quasi-reductive Lie superalgebra with trivial even part. So then the universal enveloping algebra, in this case, is just exterior algebra on the space of G1, and we are in a situation of studying finite-dimensional modules over the Grassmann algebra, which is in fact quite interesting theory in itself. So we can slightly change this example by throwing in G0. So we now have G1, which is module over some algebraic reductive group. But we still assume that the commutator of G1 with itself is 0. So those are two examples which very universal, but they are also kind of trivial, and I can't say much about it because what I'm saying is very general situation. I just have reductive algebraic group acting on G1. So what I can say about orbits, not much, except that the invariance of G0 action is finitely generated group. It's finitely generated ring, sorry, Noetherian ring. So now there are examples which come from classification of simple Lie superalgebras. And so the next examples here, they're so-called classical supergroups. And Lie superalgebras, and the algebra of automorphism of some vector space, supervector space, special linear group given by the condition that the Berezinian is 1. So if we start with, so all of these examples of classical arise from considering a supervector space with additional structure, like even symmetric form. And the example would be what is called orthosymplectic superalgebra, periplectic superalgebra, when we have a superdimension C and N, so it's even and odd dimension are the same, and an odd symmetric bilinear form, and so-called queer or isomeric supergroup Qn, when again, it's basic supervector space we start with, has dimension Nn, and it has an odd involutive isomorphism. In addition to this, so all these examples are coming from classification of Katz, who classified all simple complex Lie superalgebras, and we also have some interesting example of exceptional supergroups. We have two exceptional supergroups and one series depending on a parameter. Well, not all simple Lie superalgebras are quasi-reductive alone, but most of all are. So now what I'm going to do next, I'm actually going to So what is the goal of situation? I have X and G1, and I would like to construct functor Fx from representations of supergroup G to some other category, some other tensor category, using the construction of semi-simplification. So now I briefly remind the construction of in the theory of tensor categories, there is a construction of semi-simplification, and I briefly remind you what it is. We start with an abelian k-linear category. Sometimes the categories which I'm going to describe are called Pretanakian, and they are related to generalization of the categories of algebraic groups, basically. So it's abelian category, monoidal, with this additional condition of endomorphism of. So we work over the field K, and they usually assume that K bar is equal to K. In our case, KC. So it is symmetric monoidal category. So we have an isomorphism, functorial, such that it's involutive. If I take the composition, I got the identity, whatever I have. So what we are talking about here, we're working in the category of supervector spaces. So if I want to consider the symmetry, when there is a sign rule which appears here when we work in the category of supervector spaces. This is our main example. So in addition, we assume that our category is rigid, so it has a duality functor, and satisfying these three conditions here. So you can always think about vector spaces as one of the possible examples. So we have the maps, evaluation and co-evaluation or trace, satisfying this condition. And the one remarkable property of such categories is that we always have the notion of dimension and trace. And the dimension and trace take values in our ground field. And the example of, the main example of representation of supergroup, which we discussed, this categorical trace, it was called super trace. And it is given by the formula that when you have an endomorphism of the vector space, and you would like to take the trace, so you take the trace of even part and subtract the trace of odd part. And I should say that in our category, all morphisms are actually parity preserving morphisms. So everything is Z2 graded and the parity is preserved. So the main example of such category, and why it's called Pretanakian. So suppose I have a tensor functor from this category to the category of supervector spaces. Then my category is a category of representations of some supergroup. It might be the pro group, but anyway, there is such a thing as Tanakian formalism, which works on the category of supervector spaces as well, and was developed by Deligne and Milne. So what is semi-simplification? So now we have this category which has the notion of trace, and we are going to consider the ideal of morphisms, which is called ideal of negligible morphism. So we call a morphism between two objects negligible if whenever I compute the composition with any morphism in the opposite direction, the composition for any morphism from W to V, the trace of composition is zero. It's not very difficult to see that the set of negligible morphisms is an ideal in the set of morphisms, and we can take the quotient. And this new category which we get is going to be, again, the same category for all the same properties, but it's going to be semi-simple. And this is called and we have a canonical functor from A to A star, because what we are doing, object of our new categories are the same, but the morphisms are going to be the quotients by this negligible morphism. So a few things about the semi-simplification functor. Isomorphism classes of simple objects are in semi-simplification are in bijection with isomorphism classes of indecomposable object in A of non-zero dimension. If characteristic of K is 0 and G is a supergroup, and I take the category of finite dimensional representations of G and semi-simplify it, then there is another linearly reductive supergroup, but it might be progroup, it might be not finitely generated category, but such that the semi-simplification of the original category is the category of representation of this linearly reductive supergroup. And such supergroup is called reductive envelope of G. So I just want to mention that if characteristic of K is positive and greater than 2, and I start with, say, finite group and take the semi-simplification, then the above is not true. So the resulting category which we get is not a category of representations of some group or supergroup. And the simplest example, if I take cyclic group of order P, and if I semi-simplify it, then I get something like Verlinde category, which is not a category of representations of any group. So important example in this case is that we consider characteristic of K0 and consider just additive group of a field, consider representations, and take the semi-simplification, the result. So the reductive envelope of GA is going to be the group SL2. So, and actually Ettinghoff and Ostrich noticed that using this computation, one can actually give another proof of Jacobson-Morozov theorem that every nilpotent element in a semi-simple Lie algebra can be embedded into SL2 triple. And this embedding is unique up to conjugation, very well-known and important theorem. So before I go further, I would like what I'm going to do. I'm going to use this semi-simplification functor as a way to associate to every odd element certain symmetric monoidal functor. So let me give you a few definitions. So suppose G is a quasi-reductive superalgebra, and I take an odd element, and I take its commutator with itself. This is an even element, and this is an element in a reductive Lie algebra, and therefore it has a Jordan decomposition. So it is semi-simple part and nilpotent part. So if nilpotent part of Y is 0, then X is called homological. And in this case, and only in this case, the corresponding supergroup, which I defined in the beginning, the supergroup generated by X, is quasi-reductive, should be quasi-reductive here. So the opposite situation, if YS, the semi-simple part of Y, is 0, then X is called nilpotent. And it's actually X nilpotently on any representation of the supergroup G. And if both Ys and Yn are 0, then this element clearly is called self-commuting, which this term is clear, right? It's called self-commuting, and it's both homological and nilpotent. So let me start with the following first, our first theorem. That if, and so what I can do, I can take this G of X, and if X is homological, and I would like to consider semi-simplification of the category of representation of G of X, this is going to be just a category of supervector spaces. But if X is nilpotent and not self-commuting, then the semi-simplification is going to be OSP1 true. So this is very specific and very importantly supergroup and superalgebra, which I'm going to discuss on the next slide. So what is this? Lie superalgebra OSP1, 2. So this is actually the small, simple Lie superalgebra with non-trivial odd part. And the category of representations of OSP1, 2 is completely reducible. And then actually, it's you can describe all irreducible modules. And description is very nice. It's similar to description of all representations, finite dimensional representation of SL2 over SL2. So it has five, it's a 5-dimension, total dimension is 5. And this, so basically what we have the standard generator. So even part is SL2. And if we have the standard triple of SL2, then we take the square root of E and F, and we get a Lie superalgebra OSP1, 2. So this is the minimal simple Lie superalgebra, and the remarkable thing is that, in a way, it is very similar to the example which I told you before, only now you start with nilpotent odd element, and when the semi-simplification is going to be the category of representation of OSP1, 2. So here is the picture. So I have this generator F, and we see how F acts. The picture, just any vertex, corresponds to the basis in my vector space. And so you see white circle corresponds to the even element of the basis, and black circle corresponds, say, to odd. So one of the important things of the situation here is the superdimension of any reducible representation of OSP1, 2 is plus or minus 1. So here what is pi of V4? So this is an example of V4, which is total of 5-dimensional, even dimension is 3, odd dimension is 2. And here is the change of parity. I can start with an element which is odd, and then dimension is going to be 2, 3. So here dimension, super dimension is 1, and here it is minus 1. So what we are going, finally, we come into this functor, which we denote by Sx, and we associate this functor to any x in G1. So what we are doing, we start with representations of G. We restrict it on the subgroup Gx, and then we take semi-simplification. As a result, we are going to get in the category which is, as we discussed before, so always can consider it as a subcategory of representations of OSP1, 2. So this is the symmetric monoidal functor, and depending on the properties of X, we have different possibilities for this symmetric monoidal functor. So, and before I go further, I would like to explain how we compute this functor actually on and some particular G module. So we start with considering the Lie superalgebra generated by X, but we add, so it contains X and Y, which is the square of X, and we take semi-simple part of A and nilpotent part of A, and they compute with X. So this G of X is still a abelian superalgebra. So now what we do, we take our module over G, and we restrict it for this superalgebra, and it decomposes into direct sum of indecomposable modules. Ys, semi-simple part, X semi-simply, and since Mi is decomposable, Ys X on each indecomposable summoned by multiplication by scalar. And if the square is not 0, then the super trace Y is a commutator of X and X, so its super trace is 0. And so it automatically implies that super dimension of Mi is 0 if lambda I is not zero. If lambda is I is zero, then X is nilpotent Jordan block. And we have three possibilities. So we have the possibilities as before, but we can have something like this as well. So we look how X is acting. So this is just X of X. And so if I start with the even vector and I get odd, even, odd, so we can have dimension, super dimension 0, 1, and -1. So in the conclusion, what we do, we first take invariance over ys, because we're only interested in the case when ys acts by 0 on M. And then we can consider MYS, and after that, we do semi-simplification over there. And this way, we can reduce computation of the functor Sx to the case when X is nilpotent. So the next thing, our next result is the following. Suppose X is homological. That means that the nilpotent part of a square is trivial. Then, and this actually, this theorem explains the term homological when it is actually just, I take the invariance of ys, and then x squared is 0. And therefore, I can take homology of this operator x. And so this is actually some functor which computes some homology here. So let me speed up. So there are certain very important applications in my other work with Pevtsov and Sherman, which actually we call it projectivity detection. So a module M in rep G is projective and if only if Sx of M is 0 for any homological x. So this is the way. This is a way to figure out when the module is projective. So now, very quickly, I'm going to the case of neat elements and superanalog of the Jacobson-Morozov theorem. So we consider the ideal of nilpotent only nilpotent element, and inside it, so it's closed G0 stable conical variety. Inside it, I consider as another cone of self-commuting elements. For every x, we denote by OX the G0 orbit of x. And one clear remark that x and y lie on the same orbit when the functors Sx and Sy, which I defined before, are isomorphic. So we say that x neatly on G module M if all indecomposable Gx summands in M have non-zero superdimension, which is equivalent to that all Jordan blocks have odd length. And therefore, when I apply Sx of M, as I explained before, I don't change my vector space. Sx of M is M as a supervector space. So we say that X is neat if it acts neatly on all representations of G. And it's sufficient to check that X is neatly on all representation of G, just applying it to one faithful representation of G. And then we have this analog of Jacobson-Morozov theorem that if X in G1 is neat, then there exists an embedding of OSP1 to G, and this embedding is unique up to conjugation by the group, algebraic group G0. So there are many corollaries. For example, any quasi-reductive Lie superalgebra, the nilpotent cone has finitely many neat orbits. But this is not true in general that the nilpotent cone has finitely many orbits. You can easily find examples where it doesn't work like this. So another important and interesting condition is that the category of representation of a quasi-reductive supergroup is semi-simple if and only if all odd elements are neat. And in this case, G is a direct sum of a reductive Lie algebra and several copies of OSP1 to N. So they have some other, one more term. We call an element X and N balanced if for any M in rep G, all non-trivial decomposable summands have 0 superdimension. Okay, so if you have a Jordan block, which is not trivial, when it has even length, and this is kind of interesting result, our recent result, but you can always write any odd element as a sum of neat and balanced element, such that they commute. Moreover, if I have two such decomposition into the sum of neat and balanced, then these two decompositions are conjugate by the action of G0. So maybe I just skip this. So we have such a decomposition, and then one more thing, for using this decomposition, we have actually the map from, so you remember we have a nilpotent cone, and inside it we have a smaller cone, which is a cone of self-commuting element. And so if we take, there is the map between the orbits. So all nilpotent orbits, we have a map to self-commuting orbits. And the neat orbits are exactly the orbits which are mapped to zero. All other orbits don't map to zero. The preimage of any orbit is a finite set of orbits. And what is more important, but actually, if we would like to compute this functor Sx, that this functor can be described only in terms of the image under this map. So essentially, you take your element, which is an arbitrary, you take an arbitrary orbit, and you reduce to the self-commuting orbit. And when you consider, so self-commuting orbit is z squared equals 0. And so this is just homology of G. So in particular, there are two consequences of this theorem. The first consequence is that if you want to check if n has finitely many orbits, that happens, it's sufficient to check it on self-commuting cone. If self-commuting cone has finitely many orbits, then n has finitely many orbits. And another interesting property is that although this functor Sx is not exact, it has this nice property that whenever I have an exact sequence of modules in real G, then there exists E, an element in S vector spaces, super vector spaces, such that this exact sequence, so we have an exact sequence with 5 elements. So you can say that your Sxm is not left exact or right exact, but it is exact in the middle. Well, I think I should stop here. So I would like to say that there are several applications of this functor useful for representation theory, but I should stop here. Thank you for your attention.
Thank you. Thank you, Professor
Yeah.
Serganova.